Yeah. Okay. Thank you, everyone, to be here today. So today we have the chance to welcome Dragan. Dragan, I don't want to misspell your name, but I will try. So Dragan Stepanovic. It's like this, yeah. Okay, cool. So it's a talk regarding async code reviews and why it's killing your company's throughput. So I have seen the slides before. It's really interesting. So I hope you will be interested as well. And what we propose is to not interrupt Dragan during the talk and keep your question for the end of the talk, or stack it in the chat. We'll come back to it at the end of this session. Okay, for you guys, folks. Guys, it's a little bit sexist, let's say. Okay, so Dragan, the floor is yours.
Thanks, Jan. Thanks for having me in your lovely community. And that was one of the best spellings of my name I heard. Besides the native from the native folks. But yeah, my name is Dragan Stepanovic, and I'm going to talk about the async code reviews and the PRs. The name of the talk tends to be a bit, some people find it, or some people find it a bit strong. And I think that's fine. It should serve, I think, as a conversation starter, not as something to alienate people in a sense. And yeah, that's and I think you might find today some substance behind it, in the sense of the study that I did, that we're going to go through. So yeah, I currently work as a senior principal engineer at Throughput, which is the Delivery Hero company. And the things that I'm mostly interested in, during my career, is extreme programming, TOC, lean, and systems thinking. And these days I'm trying to connect the dots between these. And there's a huge surprise in terms of overlap between these concepts. And it seems like there's some core message in there that I'm trying with the rest of the community to crack, to understand. Like, there's different views of the same thing. And yeah, I tend to rant on LinkedIn and Twitter, and I have my micro blog that you can find if you're interested, that they usually use just for recording the thoughts, in a sense. There's also one terrifying fact about me, is that I put mayo on pizza for some reason. It just happened at one point in my life. I have no idea why and how come, but it became a part of my life. Lots of folks are finding it strange, in a sense. And if there's any Italian, if there are any Italians in the audience, I can imagine your facial expressions currently. So the thing that I'm going to talk about today, just to set kind of framing, is in this sense of just sharing, right? Which I find very important. I'm not telling you what you should do. I'm not telling you that you should do pull requests. I'm not telling you that, you know, your context is the same as mine and stuff like that. So I did a study that we're going to talk about, and I just want to let other people know about it, and, you know, if anyone finds it valuable, even better. So I'm going to start with this quote, which says, "Nobody ever got fired for buying IBM," and it's very popular in a sense of so for the folks that didn't hear about it, it's that I think during 80s IBM had a huge market share when it, as a vendor of computers and for the procurement in the companies, servers, etc. And usually people found it like people working in procurement in companies, client companies, found it as a way to minimize the downside risk if something goes wrong. So by default we go with IBM. Hey, if it fails, you know, or if something is wrong, you know, who could have knew that, and it's IBM and everyone else is doing it. So compare that to something with, let's try something else that has less market share and is different, right? You most probably would have to answer way more questions than if you go with the default option, right? So in the same way, I think our industry is also using what they call PR-based async code reviews, which, as you might know, comes from a context of open source software, and where people are geographically distributed, they don't know each other, and pull requests are something that is used in order to be able to contribute to code base of a person that you don't work as part of the same, so to say, product development team with them, right? But we have adopted this from this context into our industry throughout the product development teams, and to kind of give an example of what I mean by PR-based async code reviews for the folks that don't know, but I guess the most of you know, is that we have, let's say, a start of the sprint. Let's say a team is doing Scrum, and we have Emma and Luca here, and Emma is, starting her day. She's trying to figure out what is the next thing that she can work on. She pulls in a ticket, yellow ticket number 1, and starts working on it. And at one point, she figures out, okay, I think I'm done with this, and I would like to ask feedback from my peers. So she invites Luca to review a PR, right? But in the same way that Emma started her work, in the meantime, while she was working, Luca also started his work, ticket number 2. So when he gets a request for a review, he's busy with his own ticket, right? So it takes some time for him to get back to Emma. There are lots of other things going on, lunch breaks, meetings, stand-ups, checking email, answering Slack, reviewing other PRs and stuff like that. So at some point he gets back to her, and they go back and forth a couple of times. But now the important thing is when he gets back to her, while she's waiting for Luca to provide feedback, she, as a good worker, doesn't want to twiddle her thumbs. So she pulls in another thing and starts working on it. So once she gets a feedback, she's not able to react immediately to it because she's busy with some other things. So they go back and forth, sorry. And in this async manner, and at one point they converge on a solution that both of them are satisfied with, and they merge, approve the PR and merge it, right? So I mentioned the study that they did, and the context about the study was that I try to follow this principle, which says meet people where they are. And the idea is, everyone has their own context, has their own experience that shape their thinking, and also the culture of the team, culture of the company, etc. And I usually try to help the teams in terms of figuring out, is there any way that we can change the way that we work in order to maximize the throughput of the value of the team. So there's a when we talk about not doing PRs and talk about some other ways of working that we're going to touch upon afterwards, and those are pair and mode programming. There's a certain share of managers that are, and also developers that are interested, okay, but how does this, look like, in a sense of, do you have any data or any metrics or any indication that we should try out this way of working compared to what we are doing currently? So I started like completely lightweight study, being curious about a couple of things. And what I was curious to see is, because of me, of the fact that I come from the XP community and being encountered with the PRs and async code reviews, I had a hunch on the things that might be different in a sense. And I was really curious to see the engagement when it comes to the pull request, especially in the case where you have lack of responsiveness from the actors, the thing that we saw before. So, Emma is waiting for Luca, Luca is busy with something else, and then the other way around, right? So, and I was curious to see, well, how does this affect engagement, because the latency in the system is increasing. And one of the metaphors that I have in my head is, if you talk to someone on the phone and there's a latency involved there, the conversation tends to die off with the time, right? And the shorter the latency there is, the more people are able to conversate, so to say, right? So that was one thing. And the other thing is trying to understand how much of a wait time is there, meaning how long this item that we're working on is waiting for someone's attention, right? So I'm not talking from the perspective of individuals, of developers. I'm talking from the perspective of this work item, which at one point becomes a PR that we want to deliver to production, deliver value to our users. How much of a wait time it has, which means how long during its lead time it is waiting for someone's attention, right? Being stuck there in a queue. And how does this relate to the size of the PR, right? In terms of the complexity of the PR. So let's dive into the first one. So the first one was the engagement, and why was I curious to see it is for the thing that I mentioned about this, curious about systemic effects of delayed and choked feedback. So I talked about the delayed feedback, right? But there's also one more component of PRs, which involves the fact that most often people provide feedback in a written form, right? And sometimes people provide feedback in a verbal form, they peer review, so to say, but that means that both of the actors have to be available in order to do that, which in async systems is very difficult because people just pick up new things while they're waiting, right? So if most of the people are providing feedback in a written form, which tends to be way more expensive than a verbal form, it takes me a way longer time to write what I'm talking about currently than talking about it. Then how does this choked feedback affect, the amount of the feedback that you get and the quality itself as a proxy for that? So that's what they call high latency and low throughput feedback, right? And on the other way, there are different ways of working that we're going to touch upon afterwards. If we try to reverse this and find a way to have a low latency, and because of a low latency to be able to have a high throughput feedback, right? And when it comes to engagement, I was curious to see engagement by size, meaning as the size of the pull request increases, how does engagement look like? So let's look at the first scatter plot here. So this is a data set, I think, of 500 PRs. It's just, I think, zoomed in a bit. And on the x-axis, you can see the size of the pull request, and on the y-axis, you can see the engagement. Now, why did they go with the simple lines of code when it comes to the size? Because perhaps I'm talking about the size, the amount of the work here, right? And there isn't really linear relationship between the size and the amount of work. Why? Because you might have just a simple update of a library that generates, for example, on front end, or some npm package that generates 10,000 lines of code change, but you invested actually, just a minute of time, or 5 minutes, or 10 minutes, right? But and these are the outliers. What I'm going to talk about today is, the pull requests that are related to the the complexity of the work scales with the size, right? So there are different ways to measure, so to say, the amount of work and the complexity of the PR. Some people look at the lines of code, and people look at the number of file change, etc. But I went with this metric. And engagement, when it comes to the engagement, what I mean by this is the amount of comments that I get to see after raising a pull request on the given pull request, right? So, and here I didn't count in the comments that I call trivial. And trivial comments for me are these +1 or thumbs up or LGTM, which means looks good to me, etc. Because I don't think that they're part of the feedback in the sense of providing value, right, to the authors. So I filtered these out and got the non-trivial engagement. So this is what we get to see here, and there's not much to see here. So when you look at it, there's most of the PRs are like less than 500 lines of code and less than 15 non-trivial comments, right? But then I started thinking about it. I'm actually here measuring the engagement by size, but I'm putting on the same plane, so to say, the small requests and the big requests, right? Pull requests. So for the pull requests, it took a longer time to develop, and the ones that perhaps have a higher amount of or the bigger change in terms of the lines of code, right? It's not the same thing if I get 2 comments. If I have a work item that I spent 7 days working on, right? And it takes me, and I get 2 comments as a review. And if I have a pull request of 10 lines of code and I have two comments, right? So the amount of feedback that I get to have, also depending on the amount of feedback, right, is not the same. So what happens if I try to normalize this and say, okay, now on the y-axis, instead of the engagement, I try to see what's the engagement per size of the pull request, right? And I think there were a couple of things that I was expecting to see in a study in terms of this feeling as intuition that was built from the experience. And what I can see from this is that as we decrease the size of the pull request, or if we go the other way around, if you increase the size of the pull request, the engagement per size tends to go down exponentially, right? And this tends to be interesting, and I think it maps to what we get to hear from the experiences in the industry. And these big PRs of 1,000 lines of code and people just putting +1 or LGTM and approving, there is a reason for that, because if I get a request to review a work that took 7 days, that's already very hard to course correct, and it's very hard to build a quality at that point in time. So what we do usually, we just approve and pray that next time we'll be able to correct the things that we wanted to correct, right? So this delayed feedback incentivizes people to just give up the things because of also the sunk cost fallacy. It's also more difficult for authors to accept the feedback because they invested so much time, and they became also as part of the process emotionally attached to it, that accepting or incorporating feedback becomes a bit more difficult because of the process that is used, right? So and why I find this important is that if you look at the if we want to use pull request as one of the ways to build the quality in, right, to provide feedback and course correct, then if we're not able to get the feedback, lack of engagement meaning lack of feedback, then that implies that we're also not able to build the quality, right? The process is kind of choking the ability to build the quality in. And I'm at the same time, I'm not saying anything about the left-hand side of the spectrum, meaning you can have a lot of the feedback, but that doesn't mean that you're going to have quality, right? Because it really depends on the type of the feedback. But if you're not getting feedback at all, if the system is choking the feedback because of the incentive structure, then you're not able to also to build the quality, right? So this quote really kind of maps it. Never had a huge PR that didn't look good to me, right? About the incentives of this process. And this other screenshot, 10 lines of code, you have a lot of engagement for 500 lines of code, looks fine, right? So that was about the engagement. And now when we get into the wait time, which was way more interesting for me in a sense of surprising systemic effects that I got to see. If we go back to this visual, right, and the wait time that we see here is actually, if we focus on ticket number 1, this yellow thing, and we just see in the timeline where this item has been worked on, right? And then if you look at the wait to processing time ratio at the bottom, we're going to see that most of the lead time, this ticket tends to spend waiting for someone's attention, right? So optimizing faster development doesn't really, in a sense of typing faster or thinking faster or whatever, doesn't really help much with the optimization of the whole lead time, because if most of the time is in the wait time, then work time is not really the intervention point. So if you look at that, that kind of becomes an important thing to visualize. So how did it go about measuring the wait time, right? So I thought about it in a simple, so I had to come up with the approximation that has its assumptions that need to be validated with every repository. And by the way, this study that I did was across tens of thousands merged pull requests in a typical product development team, so not open source. So there was a huge amount of data that was involved in the analysis. And the way that I went about measuring the wait time is that, okay, if I think about how, we are when we work individually I code for some time, and then at one point in time, I ask for a feedback, and then we go back and forth until we converge. So I try to measure this from this point in time of I ask for a feedback until the pull request has been merged. I calculate this, count this as a wait time. Now there are a couple of approximations there that are and assumptions that are very important to have in mind is that the processing time or work time when you're effectively working on this item can have a wait time as well, right? What that means is that if I might be coding for it takes me from the first commit until I raise a pull request, it takes me a day, but I coded maybe only 1 hour and the rest were meetings, right? So that's kind of important thing to have in mind. But also the wait time can have processing time, right? Meaning that, yes, I calculate this wait time in the way that I explained, but what if there's a lot of feedback that I'm getting back and forth and lots of commits that I see after raising a pull request, then that would indicate that there is a significant amount of processing time during this wait time approximation that I used. So I become conscious about the results that I get to see, because then the approximation is not really as good, right? But the wait time was really important in the sense of it gave me a really way more precise or accurate accurate results when it comes to the wait time compared to the processing time. The processing time was a bit more volatile when it comes to the accuracy for different reasons that I'm not going to go into currently. So the other thing was also that processing time and flow efficiency, which we're going to dive into deeper for the folks that are not familiar with this. On the bigger size of the spectrum of the PRs tend to be a bit more inaccurate because of Git rewrite practices. What that means is that if I have if I do a Git squash, for example, and I rewrite the Git history, and I measure the processing time from the first commit until the pull request has been raised, then effectively I can do 7 days of work and squash it into a single or two commits, which are a part of 15 minutes, and calculate this as a processing time. But the process time was way bigger than that. So, and then the error margin is way smaller on the smaller PRs and of the spectrum than on the bigger ones. And yeah, the thing that I mentioned about wait time being way more accurate than processing time, which was important because the conclusions that I got were actually based only on the wait time. Yes, I mentioned this as well. So one of the results, so here's a screenshot of it. So here you can see the number of PRs, merged PRs analyzed, and it was a data set of 500 of those. And it took us, for this team, it took them 6 months to push through the system these 500 pull requests, right, from opening to close. So, and the interesting thing to see was that this approximation of the wait time told us that the wait time, cumulative wait time in the system, meaning all of these 500 pull requests, when you sum up the wait time that they were stuck in the system, you get a number of almost 28 months, which is a huge amount of wait time there, right? Now, why is this important? So if you think about, we as developers try to provide value to the customers by changing the code, right? Changing the system. So if we are not able, so if this code change is stuck in the system for a longer time, that also means potentially that the value is going to be delayed to the customers, which means a longer feedback loop, which means less learnings or the longer cadence of learnings, etc. Right? I'm not saying that every code change is bringing value to the customers or to the members of the team, but for the cases where it does, these things are stuck in the system, which means the value is being stuck in the system. So going into the scatter plot for the wait time, here on the x-axis you can see size, on the y you can see wait time in hours. There is not much to see here again, But if you apply the same thinking, right? Let's say that it takes me, let's say, I don't know, 2 hours or 2 days, 2 hours to develop a pull request, right? To raise a pull request, meaning from start of coding until I raise it. But it takes me 2 days to get a review. The cost of code review is way more expensive if it takes me 2 days, right, compared to when it takes me 2 hours. Meaning, if you think about it, the cost of code review per line of code is what becomes here important, right? So if it takes me 2 hours to review to write a PR, and I need to wait 2 days, is not the same as if I need to wait 2 hours, because there is a 50% of the lead time. There is a 50% of the writing and 50% of the getting feedback and merging and potentially wait time, right? So if we try to normalize this by the size in the same way that we think about it when it comes to the engagement, what we get to see is this kind of parallel curve, exponential one, which says for me that as you decrease the size of the pull request, the wait time per size in minutes per lines of code tends to go up exponentially, right? So you can think about it as the amount of waste that you have in the system, right? The smaller pull requests you do, the more waste per unit of work you tend to incur, right? And this is very important because I have been advocating also engineers to do small pull requests, because of all the problems with big pull requests. And I think it's a good thing to have. But if you keep working the same way in the async code review manner, then there's a trade-off that is incurred here, right? And we're going to go into what it actually means. So what for me this actually means is that as we decrease the size of the pull request and we keep the same way of working, the cost of code review per size tends to go up exponentially, right? And yes, as I mentioned, we want to have small PRs, quicker to write, quicker to review, less time allocation for reviewer, etc., right? Higher engagement, less risky. But at the same time, there's this thing that is saying to us, hey, reviewing or a small pull request tend to incur way more cost as we reduce the size of the pull request, right? And that's a really good point, time point to plug in the quote from Edward Deming. The system that people work in and the interactions with people may account for 90 or 95% of the performance, right? So saying what it means is actually the way that you design your system, the ways of working tend to shape the behavior that you have in the system, right? So, and no one is there to be blamed. Everyone is trying to do their best, right? But the system in 95% of the time, let's say the system is going to beat you. You can try to go against it, but it's going to beat you by the incentive structure that you have set up with this particular design of the system, right? So to give you another parallel when it comes to this, because I'm trying to connect it with something that is familiar to us already, that we have experience. And when you have a slow test suite, let's say that it takes you 20 minutes to run the test suite in order to get feedback from the tests, what actually kind of behavior that incentivizes, right? So I'm sure that none of us would then run test suite after every line of code change, right? Why? Because if it takes me 5 seconds to make a line of code change and it takes me 20 minutes to get the feedback, then economically it doesn't make sense to do, right? Because most of the time I'm going to spend waiting, right? And that is important because in this kind of system, if you try to reduce the size of the batch here, right, the amount of changes that you introduce to the system before running the test, the system is going to push back to you because of the incentive structure and the economics, per unit economics, that you're going to go more into the bigger batches, right? So and I'm going to write maybe I'll write a half an hour of code and then or 1 hour and then wait for feedback for 20 minutes or 10 minutes or whatever. But that also comes with a problem because now you're going into bigger batches and you're incurring all the problems with the bigger batches that we talked about, delayed feedback, harder to troubleshoot and all these things. Why this might be the case, I try to dive deeper into it, and one of the hypotheses that I have, I try to present it in this causal loop diagram that comes from systems thinking. And to give you just a short crash course on it, the labels that you see here are called variables, and there is a connection between the variables, right? There's a blue connection and there's a red connection, or blue is plus and red is minus. And for example, when you talk about the plus, right, and the connection between the variables, it says that this relationship indicates that both variables go into the same direction, right? So for example, if PR size goes down, then let's find the blue one. If number of PRs to review goes up, then the number of possible interruptions for reviewers also goes up, right? And the other way around. So that's kind of a plus. They go into the same direction, either up or down. And the minus, means that they go into the opposite direction. So if we take an example of PR size, if you reduce the size of the PR, then the motivation or incentive to review is going up, right? Because people tend to engage more and want to review smaller PRs than the bigger PRs. So let's try to walk through these loops here, trying to understand this. So, if the size of the pull request goes down, then the motivation or incentive to review goes up, right? And because it goes up, that means that the reviewers are going to respond quicker, and then the time waiting for a review from the author's perspective is also going down, right, in the opposite direction, which means that the perceived cost of code review per line of code from the author's perspective is decreasing as well, right? Which also incentivizes them to reduce if the cost of code review per line of code is going down, then there is the PR size also tends to go down. So that's one of the feedback loops, which is a reinforcing one here. This R represents this reinforcing one. And but if you look at the other side, thinking about the way this async code reviews way of working, if you reduce the size of the PR, then the number of PRs to review in a unit of time goes up, right? If you used to develop in 1 week 1 PR, and then you reduce the size of the PR, average size of the PR of a team, halve it, then you're going to double the amount of reviews, PRs to review in a week, right? And what that also means is that the number of potential interruptions for the reviewers goes up, which means that the motivation or incentive to review is going down, right? And this is kind of a conflict that I tend to see in the teams. This is a balancing feedback loop, which is actually preventing the system from going into this direction of reducing the PR size. And what this means, if you close it back, is that this balancing feedback loop is actually pushing the system into the other direction, right? So there's a conflict here, right? This motivation incentive to review from different sides. And talking about the metric that I find important here is the metric called flow efficiency. For the people that are not familiar with it, it's actually you look at the work item flowing through the system, and you calculate, you have a lead time, how long does it take from start till end, and then out of this lead time, you try to figure out how much of a time have we been working effectively on this item, right? And then we calculate the percentage of the whole lead time. The lower the flow efficiency, the more waste in the system you have, the more things are waiting for someone's attention, the more they are being stuck for a longer time in the system, right? So high flow efficiency is a metric that is important to consider when trying to change the system and optimize. And I was trying to figure out how does this thing look, because I had the lead times, I had the wait times. And one of the things that was kind of interesting to see here is, for the same data set that we got to see, is you can see that, on the y-axis, there's an average flow efficiency up to a given number, meaning that here we can see this is, for example, a pull request of, 120 lines of code, right? And the flow efficiency is maybe 17 or 18. right? And the way that I calculated it, I take all of the pull requests that have a size up to 120 lines of code and calculate the average flow efficiency, and then I plot this dot there, right? So here you can see the average flow efficiency as you decrease the size of the pull request, and it takes a hit at one point, it starts plummeting right here. Now, why is this important? I find it important because if you think about it, if you have this kind of system with this kind of results, and if you have a 300 lines of code change that you want to push through the system, right? So we have, let's say, two ways of doing that. We can split this into 15 pull requests of 20 lines of code, or we can do a single pull request of 300 lines of code, right? But in this kind of system, with this kind of behavior, what you're going to see is that the cumulative lead time for 15 pull requests of 20 lines of code is way bigger than the cumulative lead time of one PR of 300 lines of code, right? I'm not saying that these 300 lines of code are not going to incur a rework down the road because you didn't build the quality in, going back to the engagement that we got to see, but the amount of time that it takes you to push these changes through the system is way shorter. This lead time is way shorter for if you push it in the bigger batches, right? And so people are forced to, kind of make a trade-off that we're going to go into. So what this means is actually, because what we see from this example, the flow efficiency, on the left-hand side, there's a way more waste in the system, so the throughput tends to go down because the flow efficiency plummets, right? And one of the ways that I try to represent how this kind of happens, also going back to the similar structure of the diagram, causal loop diagram. So here we can see that if we reduce the size of the pull request, what tends to happen is the processing time per size tends to go down linearly, right? Or it becomes constant, right? Meaning that, if for a bigger pull request, for the ones that took a longer time, right, they take me X amount of time. But if I go to the smaller pull request, it takes me perhaps proportionally smaller amount of time to develop. Really depends on the work type of work, but the way that it scales when you drive the pull request down is per size tends to be linear or constant. And on the other hand, when you think about the wait time per size, as we saw, it tends to go up exponentially as you reduce the size of the pull request. And why? Why the difference? Because with processing time, you are only rely on yourself, right? You're the only one who writes the code, and with the wait time, actually, that's when the dependencies to other people in the team start kicking in, right? And the more other people are busy, the more wait time per size you're going to incur, which means that the wait time to processing time ratio tends to go up as you decrease the size of the pull request, which means that the flow efficiency is also taking hit, which means that the throughput goes down as well. So so we're saying that, for a bigger pull request, we lose quality on the bigger end of the spectrum, bigger size of the PRS end of the spectrum. And on the other side, for the smaller PRs, we tend to take it on the throughput, right? So that's kind of interesting, thinking about this evergreen dilemma in software development, speed versus quality or throughput versus quality, right? Always kind of trying to think about the trade-off. And when I think about this, for the folks that have read the principles of product development flow from Don Reinsher, so there's this, it becomes apparent that this is a U-curve batch optimization problem, which tries to trade off between two things, transaction cost and the holding cost. I'm not going to go into these two, but what we're trying to do in this kind of system, we're trying to find the optimal batch size to not incur too much waste and also not to incur too much of a holding cost, right? So I find it also interesting because for the Accelerate book that presented the research done, I think, over 5 years period, right? The one of the biggest myth that has been debunked in a scientific manner, right, was that it's not this assumption that it's either throughput or stability, right? But that it's not either throughput or stability, but it's the ratio is not or but and, right? So you either have both throughput and stability or neither of those. So the trade-off, I tend to hear this a lot of the time. There's always this trade-off. That is true, but there are some cases, or potentially lots of the cases that we didn't go deeper into, that actually don't exist because the underlying assumption is flawed, right? So we might have a chance actually to eat our to have our cake and eat it too. And why that might be the case, we're going to try to work back from the problem that we're going that we saw, right? So if we think about the cost of code review per size, meaning cost of review per size going exponentially up as we reduce the size of the PR, which affects the throughput, as we saw, right? So what if we try to work the other way around in order to keep the small batch sizes but not lose the throughput, right? So that's kind of a problem to solve. And if we start working backwards, if we want to keep the throughput constant as we decrease the size of the pull request, then we must have the cost of code review per size be constant or not increase exponentially as we reduce the size of the PR, right? So in order to keep the cost of code review constant per size, what we need is that the actors in the system, so author and reviewer, as we reduce the size of the PR, need to react faster and faster and faster. So they need to react exponentially faster in order to keep the cost of code review per size constant. And how to do that? Well, you might ask yourself why people are not able to react immediately. Most often because they're busy with something else, or all the time because they're busy with something else. So if we want them to react, to be able to react faster and faster and faster exponentially, then their availability needs to go up exponentially as well as we reduce the size of the PR, right? And if we try to map this into the visual that we looked at, so for this ticket number 1, and we say that we have a certain size of the pull request and have a certain throughput, right? Now, what we're saying is, if we want to reduce the size of the average size of the pull request in a team, what do we need to change in order to keep the cost of code review per line of code constant? So Emma and Luca need to react faster, right? So as you decrease the size, they need to react faster and faster. And as you reduce it to a minimal size, let's say hypothetically 1 line of code, that means in order not to lose the throughput, they would have to react immediately, right? Meaning after every line of code change as it's being typed, they are reviewing it, right? In order not to lose the throughput. So the conclusion, my conclusion of the study was that in order to not exponentially lose the throughput while reducing the average size of the pull request, people need to get exponentially closer and closer in time when it comes to the reactions, right? And for me, this kind of makes this shift from the async code reviews to the continuous code reviews, right? Providing code review immediately as it's being typed, the pull request, right? And if we look into the diagram that we looked at and this conflict here about the motivation incentive to review, the problem is that is driving this balancing feedback loop is that with the reducing the size of the pull request, if people keep working in the async manner, the number of interruptions for the reviewers and also for the authors, because they also have to react, to the feedback that they get, it goes up, right? But then the question is, what if you're not working on anything else at the same time, right? then actually you're not going to be interrupted, right? So this is a perfect segue to a portal or a parallel universe of different ways of working. And I tend to call them co-creation patterns. I'm sure I didn't come up with this term. These patterns are pair and mob programming, and I'm sure in this community a lot of you practice it and or at least familiar with. And what they tend to do when we see the cost of code review being constant as we reduce the size of the PR, actually this transaction cost is minimized because per line of code, which actually enables us to provides economics in a way that we are able to reduce the batch size to effectively one line of code, right? And I was curious to see how would this scatter plot look like had we had continuous code review, right? So you can imagine it. I didn't measure it, but I think it's impossible if you provide immediately review that the wait time is going to be more than immediate, right? Because the reviewer is immediately available. So the wait time per size would be 0 or constant, right? And engagement per size, I'm sure that it's going to be the same or even more. Why? Because this kind of way of working, because the latency is non-existent, is kind of immediate, right? It also incentivizes people to provide more feedback, which means that it can also be unlocking capability for more quality, right? So for me, it's not throughput or stability, right? I think challenging this hidden assumption there is leads us to both have throughput and the quality, right? And I know this sounds in a way as some kind of utopia, right? But what I got to understand is why the short feedback loops are important. It's because they decrease the amount of rework in the system that you have, right? And that's how you get faster, right? So if you're running longer for feedback without the feedback, there's a higher and higher risk of exponentially more rework in the system that you're going to have, right? Or you're just going to push this thing through the door and kick the problem down the road because it's going to bite you afterwards with the outages in production and the other problems, right? Maintainability and stuff like that. So as the last part of the talk, I'm going to talk about these kind of metrics that I was thinking about, which I call PR score here. And you might have noticed it on the right-hand side, right? The way that I came about it, and I think it's kind of interesting, is that asking ourselves, what are we trying to optimize for when we think about the review process, right? So we want the size of the pull request to go down for known reasons, right? But we also want to have the wait time per size minimized or going down, right? And for the reasons that we talked about. And also we want the engagement to go up, or at least not to go so low that then you don't have quality at all. So I was thinking, okay, if we optimize for these things, can I put it into a formula? So the way that I did it is size times wait time in seconds divided by 1 plus engagement. 1 plus because on some PRs engagement is 0, right? So I don't want to divide by 0. No one wants to do that. And what I got to understand is that, how does this look with the pair programming, for example, and mob programming, these mechanisms that provide you with continuous code review? It's that the size of the pull request can be as low as 1 line of code. Let's say it's atomic, right? So you change a variable, it changes, in the usages and the definition, but the change is atomic. And wait time in seconds is 0 because you get to have immediate feedback. And the engagement most probably goes up because the latency is shorter, and that incentivizes actors to communicate more. So the results for for these pull requests that they analyzed were so huge when I calculated this absolute score. So I needed to do a natural logarithm of that, right? And the result, going back to result, it was 0 for the PRMO programming. And when I calculate that as a natural logarithm, it also becomes 0. So what I'm saying is actually, by this definition of the things that we want to optimize, the continuous code review and practices that enable continuous code review as a side effect provide the best results here, which is 0, right? So I was plotting this against all other pull requests. So you can see this is on the y-axis. You can see the logarithmic scale. So the distance between these two worlds is really huge, right? Just to try to visualize it, right? And to close it off, the optimal size of pull request is one line of that's a saying that they tend to have. The optimal size of pull request is one line of code that is reviewed immediately as it's being typed. And I honestly don't know for a better way to achieve it than by doing pair and mock programming that provide it as outside as a side effect of the practices themselves, right? I also try to figure out, okay, you know, if we do pair programming, let's say, and we calculate pair programming by this orthodox definition of 2 people spending twice as much time on a single thing, you know, even if we think about this orthodox definition, how would the results look like compared to the initial ones? Well, the wait time is going to be 0, right? But I double the processing time. So the cumulative lead time or the how many times sooner would it be finished here was 3.3. The results are not really precise, but it doesn't really matter for me. The purpose was just to see the magnitude of differences, right? In order to be able to consider different ways of working. And yeah, delivering code sooner enables delivering value sooner, which means reacting based on the feedback sooner, and shorter learning cadence and faster iterations, and achieving business outcomes and customer success sooner, right? So last slide. We've been told all along that we'll achieve more if we limit and delay our interactions. But I hope that you now also have a data-informed reason to perhaps consider other ways of working and not take it as granted. And with that, I would like to thank you for your time, for coming, and yeah, we can open the floor for the questions.
Yeah, thank you, Dragan. It was really interesting. Yeah, we had some questions in the chat, so yeah, maybe we can start by the first one. Daph, you have one question for Dragan. Are you still there? Yeah, because we had some disconnection, so I don't know if you are still there.
Yeah. I've noticed. Let me see if I can get this working. There we go. Hi.
Yeah.
Yeah, I've noticed in a lot of teams. I mean, I come from an XP background, but I notice in a lot of teams there's an assumption that they use Jira, and there's one story, and there's one PR, and then there's a review, and it gets merged in. So it's very simple if you're managing projects to think of a story as being just one thing that you merge in, and either it's in or it's not in. And to me, that seems very unrealistic. I mean, if you're doing DevOps, you could be working across a lot of projects. You could have maybe 4 or 5 different things to merge in. So one of the things I wanted to do is to have more than one PR per Jira, per story. So I'm kind of wondering, do people agree with me or not? It's certainly, I would prefer to have multiple if I have to have branches and PRs, I would rather have more than one than have one mega thing that I have to push in all in one go. So project managers seem to love the idea of, well, we can merge it in or not merge it in, but I don't think that they see the complexity of reviewing a PR, and they never see merge conflicts. Yeah,
if I was to comment to that, Yeah, I guess it's kind of easier for in that sense to track, this work.
Yeah.
Like if it's passed into multiple things at the same time, like figuring out like what is merged, what is not merged, and I guess it becomes difficult. But definitely there's this other thing that kind of incentivizes, depending on the way that the team splits the stories, and if they're able to slice it appropriately to be a really small chunk, then they're risking also a big batch, so to say, introducing the change in a one huge batch, which introduces a risk for stability of the system. But I guess that's a story that connects to the feature flags and trying to figure out can we do this incrementally, but not.
So I think you've got to
enable it.
a great analysis on the problems with batch size. I kind of, when I look at it, I think there's a difficulty in selling it to a lot of people that run these kinds of projects.
Yes, I'm very familiar with that, and I completely empathize with that, because I think as Ellie Goldberg said, common sense is not so common. It's not intuitive. I think if we define the intuitiveness by the majority of the industry, or the way that majority of the industry works, right? But yeah, I don't know. For me, it was trying to find the angles to meet the people where they are, right?
Yeah. And
trying to find the angles that can help them understand in their context, from their experience, make parallels that they can understand. So yeah, for the batch size, for example, Don Alistair talks about this story. If you need to go to the supermarket to buy an egg, you're not going to buy a single egg every time you need it, right?
Yeah.
You're going to batch, because the transaction cost is high of going to the supermarket. So if you drive down the transaction cost, the batch size can go down as well. So yeah, I don't know. I don't have an answer, but I completely empathize with that. And yeah.
Yeah, I love what you've done with this. I think you're on the right track. This is an argument I've really failed to make. I've really failed to get over what the frustration is for XP people working in the Git sort of style, especially things like Git flow. It's very difficult to explain to people what they're missing. So I come from a background where everyone was in the same room, and you commit something, and then or somebody else commits something, and before you've even pulled their merge in, they're walking across the room, and they can see what's on your screen, and you pull up the diff, and they start pointing to. So it's really, really cooperative. So it's not even the guy in my pair; it's somebody else that put the change in, and it's a very different world from what people are used to.
Yes, parallel universe. Thanks, David. And nice to meet you.
Nice to meet
in person,
you too.
so to say. Yeah.
And we have one question from Guido regarding your question. It was, should project manager have a say in how developer uses their branches? I think it was a troll, but I loved it.
Yeah, that's a good question as well.
Yeah. Maybe a last one, because we had one from Matthias, but he said he wasn't able to ask it by himself. He had to leave. So maybe we can take the one from Ravi. Ravi, are you still there? It was a question regarding mob programming. Yeah. Could you unmute yourself?
Hey, can you hear me now?
Yeah.
Sorry, I was talking on mute. Hey, Dragan, first of all, thank you so much for such a great talk. I really like the way you drew your feedback loops, by the way. That's awesome. My question was, when we're talking about mob programming or just pair programming, it's not just you sitting at your computer and just like really focusing on something and trying to get it done. You now have, I would probably call it distraction as well, of just listening to the mob or the person you're pairing with and sort of continuously addressing their concerns and the continuous feedback they're giving you, which is nice from a quality point of view. But don't you think that also kind of pushes the throughput down? Because I know we're not talking about developers across time zones and anything as drastic as that, but then it still takes more time to get something done compared to the other way around. Just wanted to get your take on that.
Sure. Yeah. That's a good question, and I tend to get it quite often. when we talk about productivity of developers, we often have this a bit, I would say, narrow view of, when is this thing done, right? So if you think about it, like, because of the incentive structure with the system that is set up, usually you don't get the amount of feedback, as you saw, that you would need to get, right? So if you were to have the right amount of feedback, and I think co-creation and continuous code, you enable this, then it can be perceived as taking longer time, right? And so I think these two things are not currently measurable, because there's a different behavior that is incentivized in different ways of working. But if you look on the kind of longer time scale, in the sense of a work item being coded and then back and forth and all of these things, and potential problems downstream in production, because only one person reviewed your code, and the PR was really big, so they didn't really invest their time to review it. That means that the lack of quality or lack of feedback being given is also providing less of quality, which means downstream rework and all the things. So I think we need to think about the lead time of things being done from the start of work until this thing is really working, right? So if you have outage afterwards in production for this thing is not yet done, right? So this thing is done when it passes the expectation that we had of it when we started working. So I think that's perhaps important thing to have in mind. And I know it sounds very counterintuitive, but for me, in my case, and I don't say that you should do it. I think you should. I don't think you should do it. I think it can be valuable to consider experimenting with this way of working. But the amount of rework is just like so minimal that having like one very trivial bug per 6 months or per 1 year allows you to go fast, because there's like very minimal rework there. So yeah, that's kind of my take on it. I'm not sure if I was able to answer fully.
Yeah, no, absolutely. That does make sense. Thanks.
Okay. Yeah, I think we need to close here. Once again, thank you, Dragan. Thank you for your thank you for your time. What you need to know is that Dragan is in transit in Dubai. So thank you for your time, really sincerely, because I know you were a little bit worried about the timing, and you did a rush, a sprint to be there in time. So thank you for that. Thank you all for being here, and yeah, see you next time, guys. And yeah, don't miss the next event. It will be on TDD, so test-driven development. We'll have the chance to welcome Salim Siddiqui, has written a book on it. So yeah, and he will explain why you can make a relationship, a strong relationship between trust and confidence and TDD. So it will be really interesting. Thanks again, Dragan, and see you next time.
Thanks for coming.
Enjoy your mayonnaise on your pizza.
Thanks. Yeah.
Thank you, guys.
Thanks.
Thank you.
Bye.
Bye.